Okay, so in the next three lectures, I'll be talking about something called Okounkov bodies, and I think this subject is very suitable for this kind of summer school because this area is relatively new. It's been only about 10 years, and there are still many questions unanswered. And because I think the statements are easy to understand, even for graduate students. So I hope you can learn something from my lectures. So. So everything is based on those three papers I mentioned in the abstract. So one is by Lazarsfeld and Mustata, and two more papers by myself and my collaborators. Okay. So as usual, I'll be working on a smooth projective variety defined over C, over complex numbers. Okay, and I use divisors defined on this variety X, and Di are prime divisors, and Ai are coefficients, but they can be integers, rational numbers, and even real numbers. Okay, so I will state which coefficient I will use in the statement. Okay, so divisors are very fundamental in algebraic geometry. I think all of you know this. Okay, so divisors are fundamental object in algebraic geometry. So there, of course, there can be many reasons, but I think the most important reason is because they define maps between varieties. Okay, because they define maps between varieties. Okay, like matrices define vector linear maps between vector spaces. Okay, so that's why matrices are important in linear algebra. But in algebraic geometry, divisors define maps between varieties. So I think, for me, this is the most important reason to study divisors, especially in birational geometry. If you read papers in birational geometry, so all they talk about is divisors. Okay. Okay. So we will study divisors. Okay. So, and there are many ways to describe divisors. For example, you can define effective divisors. So this is when the coefficients are all effective. Okay, and ample. I will not define all of these, but when the linear system of some large multiple defines an embedding, you see it's ample, and you can also define nef divisors and big divisors, pseudo-effective divisors. Okay, and so nef divisors are limit of ample divisors, and pseudo-effective divisors are limit of big divisors. Okay, and what else? Okay, and you can also attach some integers. So I will define these later, today or some other lectures. But E-taka dimension, numerical E-taka dimension, they are integers. Okay. Okay, and you can also attach some constant called Seshadri constant. And so next one is so the next one has many names. So I call it Nakayama constant, but some people call it Nakayama Fujitan. Anyway, so constant. And sometimes it's called pseudo-effective threshold. And I will also define this later. And there are many other invariants attached to divisors. Okay. So what we do in the theory of Okounkov body is the following. So you are given a divisor D. Okay. And let's say the dimension is I used D or N, which is N. Okay. Dimension is N. Okay. So you are given a divisor D, and I will construct some convex set, which is in the n-dimensional Euclidean space. Okay? And this is called the Okounkov body for given divisor D. Okay? So what we do is we want to study all these properties just by looking at this object. Okay? So we are interested in how these properties are encoded in the structure of this Okounkov body. Okay? Okay. So this is the philosophy in the theory of Okounkov bodies. Okay. Okay. And actually, recently there are I hear some very nice applications in case stability, or I will talk about this later. But there is some relations to Itaka conjecture, Nagata conjecture, and so on. Okay? So hopefully in the near future, you will see some nice applications of this, of the results in Okounkov bodies. Okay? Okay, so any questions? So this is a short introduction. Okay, so let me begin. Okay? So it's a construction. Okay. So actually there are a few different constructions, but of course they are all equivalent. So the one I give here is the shortest and I think the easiest to remember. So before I do this, let's fix some notation. So if I write this wave, then this is if d minus d prime is the divisor defined by some rational function. Okay, so if I write q here, then if md prime for some integer, and if I write r, then if d minus d prime is the r is r. So this is called linear equivalence, Q linear equivalence, and R linear equivalence. And I will use one more. This if d c d prime c for any curve c on x. Okay. So this is called the numerical equivalence. Okay. Actually, these may be familiar already. But anyway. Okay, so for example, if I write dq, then this is called the Q linear system. So this means d prime d q d. Okay. So if I put r, you know what it means. Okay. Example. Okay. So let's see how to construct the Okounkov body. Okay. So it's constructed in 3 steps. Okay. Step 1. Okay. So first, you need to fix on admissible here. Okay? It's a sequence of irreducible subvarieties of X. Okay, so X is, you are given a variety X, and this is Y0, because codimension is 0. Okay, and Y1, Y2, Yn. So Yi are irreducible. And codimension is I in X. Okay? So the dimension decreases by 1. Okay? So this is codimension 1, codimension 2, and the last one is just the point. Okay? And one more condition. So and smooth at X. Okay? So originally you need the smoothness only at this point, but actually this is not important. You can always resolve singularities, and you may assume everything is smooth. Okay? And actually the Okounkov part does not change. So shape doesn't change. Okay? So this is called the admissible peg. Okay? So this is the first step. This is the important step actually. Okay? Step 2. Define a function. Define. So your domain is one of these linear systems. So let's use Q. So okay, Q. Or you can change this to R. It's not. Okay. Actually, even you can change this to the numerical equivalence. But, okay, so this you define a function, and actually you will get non-negative numbers, coefficients. Okay. So how? So this is the set of effective divisors. Okay. So if you are given some effective divisor, your domain, your image should look like. Okay. So new one is nothing but the coefficient of di at the prime divisor y1. Okay. So your effective divisor looks like this. Okay. So if one of these is y1, then you just take the coefficient as new one. Okay. This is easy. And for new 2, you subtract all the y1 component from your given divisor. Okay? So this is a divisor, but it no longer has y1 in the support. Okay? And you restrict it onto y1. And now this is a divisor on y1. Yeah, it's a divisor on y1. Okay? So this divisor may contain y2 in its support. Okay? So you just take the coefficient. Okay? You just repeat until you get the last coordinate. Okay? Okay? So I don't need to do the next step. Okay? So this is a function depending on the choice of the admissible flag. Okay? Okay, I wrote too big, so let me use this. Okay, so in the next step, we can now define the so-called Okounkov body. So first, you look at the image. Yeah. look at the image, and this is a subset of N, and all, because this divisor is effective, so all the coordinates are non-negative numbers. So that's why you have here. Okay? And this is just a set of points. So there are many points. Okay? So so you need to take the closure of the convex full of this. Okay. So this is a set of points, and you take the convex full, and you take the closure. Okay. So this is called the Okounkov body. Okay. And the notation is this. Of D associated to y. Okay. Okay. And in some papers they put Newton Okounkov body, but they are actually the same thing. Some people put this because it looks cool, okay. But there's no difference. But actually, the points are already dense in the Okounkov body. So actually, you only need to take the closure. Okay. It's enough to take the closure. Okay. It's already dense. Okay. Any questions? So it's easy. So if you remark. So if you have already read the paper of Lazarspeld and Mustata, the construction so let's write this in Lazarspeld and Mustata's paper. They use sections of line bundles to define this function. Okay. But so it looks different, but eventually you get the same thing because the divisors and sections are always interchangeable. Okay. So, but I found that this is the easiest and the quickest way to construct Okounkov. Okay. Okay. Any questions? So far it's easy, very easy. Okay. Okay. So let's look at some basic properties. But before that, so this was originally defined by Okounkov by himself in the 90s, mid-90s. But of course, he didn't expand the theory. He just used this construction in one of his, I think it was just a lemma. He constructed this and he obtained some results. But later, only about 10 years ago, Habe and Kovansky studied this more systematically. And then Lazarspeld, they construct this Okounkov body only for very ample divisors, very ample line bundles. But Lazarspeld and Mustata, they generalized the construction to more general divisors, big divisors. And then recently I took it to the limit. So I also extended the construction to the pseudo-effective divisors. So I will explain all of this later. Okay. Some basic properties. So of course, by definition, this is closed, but it's actually also bounded. You will not get unbounded Okounkov body. Okounkov body is always bounded. Okay? And I already did, but this is Q is dense in the Okounkov. Okay? So these points are called the valuative points. So valuative. Okay? So if you take the closure, you get non-valuative points. Okay? So this is dense 3. So of course, the shape heavily depends on the choice of your flag. So it depends. This is obvious. Okay? So people try to find some canonical choice of the flag, but it's not easy. Okay, it's 4 and some formal properties. So it's additive. So D plus D prime is contained in. So this is the Minkowski sum. Okay? So this satisfies additive property, and it's homogeneous. So AD is okay for A. Okay. So first you define for Cartier divisor, and then you can extend the construction to Q divisors. Okay. But from the beginning, I already used Q divisor. Okay. This next one is actually a theorem, very important theorem. It's numerical. So this means if D and D prime, so this at some point I need to assume. So let's assume big. So D and D prime are big divisors. Okay. Big. So D is big. If H0 MD grows like M to the N for M larger. So okay. So if the two big divisors are numerically equivalent, then the Okounkov bodies are always the same for any flag. Okay. Okay. So this direction was proved by Lazarsfeld and Mustata, and the converse was proved by later by one of Lazarsfeld's students. Okay, so this is numerical object, at least for big divisors. Okay. Okay. And let me state one more. Okay, so actually, yeah, 7. It's continuous. Continuous. So let's say this way. Continuous is a function on the big one. So this is n1 x. Okay. So you collect all the big divisors and you form a convex cone. Okay. This is called the big cone, and so you fix the flag and you can move around this divisor b, and the shape changes continuously. Okay. Okay. And using this, sorry, this you can just say the set of all the numerical classes of divisors. Okay, so first, you define this for Q divisors by using this continuous property. You can now define Okounkov bodies for R divisors. Okay, so this is where you need this property. Okay. Can define for R divisors. Okay, so these are some very basic properties. Of course, there are many more properties, but okay. So let's look at some examples. Let's example 1. So in dimension 1 case, so when x is a curve, D is a divisor on x of degree D, and you need a flag, but in this case, flag is just a point. You only have y1, which is a point. But in this case, the Okounkov body lies in this real line, and it's easy to see that it's just this interval. This is D. Okay. This is almost obvious. And 2. So let's go to the higher dimension case, dimension 2. So I want to have some pictures here. So let's have it. Okay, so the setup is, let's have P2, and D is a line, and flag, so Y1 is just, Y1 is a line, and Y2 is a point. Again, it's easy, very easy to see that if you go through these steps, your Okounkov body will look like this. Okay. So basically, you need to find these 3 points. Okay. For this point, you consider any line which is disjoint from this. Okay, and then you get this. And for this point, you just take L. This is just new y L. Then you get this point. And for this point, you pick another line which contains the point. Y2. Y2. Okay. Then you get this point. Okay. And you now take the convex closure. But you also need to verify that there are no points above. But if you assume that there is a point, then this line, you will see that this line must have degree larger than 1. So you have a contradiction. Okay? So it's easy. It's actually an easy exercise. So this is L. Okay? And next thing we do is let's blow it up. Okay? Okay. So let's have this example too. So the situation is the same. This line y1 for the flag, you take a degree. y1 is degree d curve, and this is okay. So in this case, you took L as y1, but you can also take y2, smooth curve of degree. Smooth curve of degree d is your y1. Okay. In this case, you will see that your Okounkov. So this is 1. This is 1. Okay. 0, 1. This is 1, 0. Okay. Okay. So in this case, you will see that this is 1 over d 0, and this is 0d. This is also an easy exercise. Okay. And next, let's consider the blow. X is the over P2 at some point X, and D. So let's have this. This is the blow, and as your D, you consider the pullback, and you have exceptional curve. So Y E. This is your Y1, and take any point. Okay. And this is also an easy exercise that to see that in this case you will get this inverted triangle. Okounkov body of this pullback. Okay. Sorry, I'm sorry.
The linear system with R, can you give an example when they use not
R, which is not closed, non-closed. Which is
these examples, the image is closed?
yeah, already closed. So in many cases, almost in many cases, they are already closed. Okay, so I cannot remember what's. Which one is? So I'll find the example. I know some references. But, yeah. So anyway, so this is also an easy exercise. This point actually goes to this, and this, if you blow up this divisor, it goes to this point. Okay? And you get this inverted triangle. And one more. So maybe I should. And so in this last example, you add some effective divisor, then your Okounkov body will look like this. A. Okay. You can shift along the first axis if you add this divisor. Okay. So these are very simple examples, but they already shows very important properties of Okounkov bodies. So what properties do they have in common? If you see for these four examples. So if you compute the area, they are always 1/2, 1/2. Okay? Okay? So base is 1, height is 1. So, and this is 1/2, 1/2, and so on. Okay? And how about, so what's the difference between this and this? Between these three and this one. So if you see the original divisor, this is not NEF. But all these divisors are NEF. Okay? So, and they all contain the origin. So later I will show that if for any flag, the origin is contained in the Okounkov body, then the divisor is NEF. Okay? And if you see these two, so this divisor is ample, so it contains some neighborhood of the origin. But because this is not NEF, it only contains the origin. Okay? So this is already shows some very important properties. Okay? So I will make this more precise, maybe tomorrow. Okay? And what can you say about this? Yeah. Any questions? But I'll be honest, it's very hard to compute Okounkov bodies. So there are not many examples, explicit examples. Okay. So, yeah. So, and there's actually a theorem by Lazarspeld and Musata. At least in dimension 2, you can find the explicit defining equations of the Okounkov body. So X is a surface, smooth surface, and D is a big divisor. And we know that on the surface, there is a Zariski decomposition. Okay, but so D, so C is some irreducible curve. D minus TC. So you subtract some curve C with multiplicity T, and you consider the Zariski decomposition. Okay. And T ranges from 0 to some. So if T is large enough, then this is no longer big. So you subtract T until you get non-big divisors. So this is called the pseudo-effective threshold. But so anyway, so you want me to define? Okay. So this is so D. Let's define it here. so D is on surface. Okay, D you can decompose into two divisors, and D N is P. Let's describe P first. P is net. Okay, and N is effective. Yeah, it looks like this. AI is effective, and with these curves, you can define the intersection. So you can find the matrix formed by these intersection numbers. Okay, so one component is the self-intersection number of N1, and so on. Okay, so Ij component is the intersection number of I and Nj. Okay? So this is negative definite. And P and I itself, it's trivial with respect to this. Okay? So this is called the Zariski decomposition. Okay? Negative definite. So you are saying, so I'm sorry, what was your question? Negative definite. Okay. The point is that, so you see, you have many kinds of positivities, but in many cases, all the positivities are transferred to this P. Okay, so in many cases, you can just remove this, and this is useless divisor. Okay, so this is the principle for Zariski decomposition. Anyway, so at least in dimension 2, we know that there is always a Zariski decomposition. Okay, so in dimension 2 case, so the Okounkov body is a convex set, so it looks like this, and you know the left, this is so I'll just say briefly. So this is the Okounkov body of the divisor D, where Y, your flag is C, and the point. Okay, so this C is your Y1 in the flag. Okay, and this is the Okounkov body. Then you can actually. So I'll just say like this. There is an explicit equation for these two lower bounds and upper bounds in terms of Zariski decomposition. Okay. So you can find explicit equations. So it's not too complicated. So, but in higher dimensions, even in dimension 3, you don't get the Zariski decomposition in general. So you cannot come up with this kind of explicit equations. You mean the rationality? Yeah, yes. 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 So next thing is about the rationality. So all the examples you see are rational polytopes. That means the vertices are rational points. But this is not always the case. There are also non-rational polyhedral Okounkov bodies. so
These equations, they are defined by PT and T. I don't understand what we need PT.
yeah. So this is x is t. So you move this t.
Okay. So it's three-dimensional pictures.
Sorry.
Three-dimensional. So because delta is two-dimensional or anything like
So the equation is like this. So you have the explicit equation is alpha t odd of x and t c. This is beta t alpha t plus c pt. Okay, and this is the left end is the multiplicity of y1 of c, and this is the so-called pseudo-effective threshold.
so the flag.
Sorry?
What is the flag?
Flag is this.
So this curve at any moment.
Sorry.
The vertical line is T.
Line is. I'm sorry.
The vertical axis is T.
T.
So the fibers are your provided, which depend on T. There should be two-dimensional. No. What is this picture?
What is the picture?
I don't understand the picture. So for every T we have an Okounkov line.
So this x is a t.
Yes, and suppose we fix the T, then
So
yes, and what is the fiber? What is this intersection? It should be Okounkov body for T.
for curve.
But the curve doesn't depend on T.
I don't know what.
Probably the question is why T is equal to U1.
Mm, why? how to say? So first of all, how about, so you understand these two left bound and,
No, I think why T is new one?
y is t. So for example, just,
Basically, I understand some, so it's just some reconstruct.
so let's, so, so,
So I have one question.
so you can just, so you can verify this fact. So just take any effective divisor from this. Then it looks like this. So this is D, and D prime will be effective. You just evaluate this divisor by the function, this function. And you need to check that the first coordinate should have T. Okay? Then, so you evaluate this divisor, then you just check that the first coordinate must come T. Okay? So for this, you can avoid this divisor. And you don't get any multiplicity here. And here also. Okay? And the TC is TC is only evaluated by this divisor. And this is why you. Okay. And from this, you already have A. So you already obtained this T. So actually, from this definition, if you evaluate this D, then so anyway, so you will get T and something. This is okay. Yeah. So I was also confused. Maybe nervous. Anyway, so I will. There are also non-rational polyhedral Okounkov bodies. So in these examples, all the Okounkov bodies you see are rational polyhedral. But there are also non-rational polyhedral Okounkov bodies. Even even when X is a Moridian space and divisor is empty. So even in these situations, if you choose very bad flag, you will get non-rational polyidral Okounkov bodies. So there is also one example in this paper, and there's also another example by Kronia, Rozovano. And also, there are, so all the Okounkov bodies are full dimensional in R2 in this case. But there are also non-maximal dimensional Okounkov bodies. For example, if you take divisor D as the exceptional divisor in that case, for example, then in the exceptional, then your Okounkov body is just a point. Okay? Where exceptional on the block. So, I mean, the shape of the Okounkov body is almost random. Okay? It can be almost any shape. Okay, so now, so let's, in the beginning of the lecture, I listed some of the properties of the divisors. Okay, so let's extract the dimensions of the divisors first. Positive. Okay, so since we know how to construct divisors, let's extract some of the positivity properties from the Okounkov bodies. So the first fundamental theorem in this area is by, again, Lazar's-Bell demonstrator. Okay, so this again a big divisor. Big divisor on X, and we know that our Okounkov body is some subset of Rn. Okay, and they show that the volume for any flag Y. The volume of the divisor D. So let me define this. This is the lim in. So actually, you can just say it's a limit. Lim H0 MD MD. I'm sorry. H0 MD M N factorial. So this is called the volume of the divisor. So this volume is actually equal to the Euclidean volume of Rn to D. Times n factorial. So the volume of the divisor is precisely equal to the Euclidean volume of the Okounkov body, up to this constant. So if the volume was originally defined without this n factorial, then everything is perfect. But original definition contains this n factorial term. Okay. So this means that for big divisor, we know that this is always positive. And this also shows that the Okounkov body of the big divisor is always three-dimensional. Okay? So the point is, so when you change this flag, the shape also changes, but the Euclidean volume doesn't change. So this is important. Because on this side, it's independent of the flag. But here, it depends on the flag. Okay? But the volume doesn't depend on the flag. Okay? Okay. So, okay. So, maybe I can say briefly about this proof. Proof is very interesting, and it's not too difficult, actually. So actually the idea. So I summarize this as 3 steps. Okay. 1. Okay. So for simplicity, let's assume D is Cartier. So integral divisor. Okay, and also B. Okay. And the first, so you need to observe these 3 things. So first one is about the alternative construction. Okay, alternative. And this observation is also sometimes useful in many situations. Okay? So Okounkov body can be defined in the following way also. So because our divisor is Cartier, so first you look at this image. So this is the usual linear equivalence linear system. Okay, so this only has the integral Cartier divisor, and you look at the image. Okay, and so I visualize this here. So this is m equal 1, m equal 2, m equal 3, and at each step you have Rn. Okay? So when n is equal to 1, you have some points here. Okay? When m is equal to 2, you also have some points here. When m is equal to 3, you also have some points here. Okay? And what you do is, so the origin is somewhere here, let's assume. So, okay, you form a closed cone spanned by all these points. Okay? And take the union, and you form the cone, and you take the closure. Okay? So this is the cone here, the big cone, the very large cone, spanned by all these points. Okay? And then what you do is, you intersect at the level of 1. Okay, so you have Rn cross 1. Okay? This is alternative construction of the Okounkov body. Okay? So this is the Okounkov body. So to construct this, you need all these points. So, or another construction is you rescale it to level 1, divide everything by 2 and 3 and so on, and you bring all these points here and you take the closure. It's the same thing. Okay. So you observe this fact. And in step 2, you need to prove that all these, the number of points is precisely equal to the H0 of MD. Okay. So there is a lemma which says that which says that if M is sufficiently large, H0 MD is the number of the points at each level. MD cross M. But this is also equal to the number of points computed this way. M D cross G N cross N. Okay. The first equality says the number of points is equal to this dimension, and second equality says that you do the opposite. You enlarge this here, and then you take the integral point. You find all the integral points, and you count the number of points, and this also coincides with this. Okay. So this is all you need to prove this. And in the last step, step 3, and this is actually the interesting part, the volume of Rn Okounkov body is computed by counting the number of points, integral points. So the limit of the number of integral points Gn cross M N. But actually, so this part can be replaced by any convex set. And this is the Euclidean volume. Okay. So this means if you want to count, if you want to compute the volume of this, you first count the number of integral points, and then you multiply by 2, and you also count the number of points and divide by 2 to the n, and so on. Okay, if you take the limit, then you get the volume. But in the step 2, this part is actually equal to H0. Mn, and this the volume of D. So because you have to divide n factorial. Sorry. Okay, so this is what you do. Okay. Okay. So this is the main idea. So here the number of points is actually equal to the H0. Okay. Okay. Any questions? Okay, so now let's focus on the dimension now. Okay. So in his paper, it's not explicitly stated, but you can easily see that D is big if and only if the dimension of the Okounkov body D is n. Okay. So this is easy to observe. Okay. And to talk about the dimension of the divisor D, so let's have some definitions. So the first one is called E-Taka dimension. This is the maximum of K H0. Here. It's not big, then it's 0.
No, but you can still think of the volume
So this way is okay, right? If this is big, you know that this is positive. That means in order for this to be positive, this must be full dimensional.
Yeah, but the question is what happens when it is not big? When it is not big, it lies in some hyperplane and it has a volume in this hyperplane. So
But we compute in this volume.
yeah. So the theory is okay, but the question is, can we say more in the situation of it is not big about the volume?
Yes. We can. So you can, if this is lower dimensional, you can also compute the volume in the hyperplane. It has also meaning.
So the volume is appropriate hyperplane also does not depend on the plan.
In this case, in the lower.
But the question is, when it's not big, it's lower dimensional. We can still talk about the volume.
Yes.
Is there a similar statement?
Yes. That's what I want to state. Also, the dimension has also meaning. It computes some dimension of the divisor, which I will state here. Okay. So the Ithaka dimension is md and the k. All right. Okay. So whenever this is non-zero for something, okay, if this is all zero, you get negative infinity. And there is also called the numerical Ithaka dimension. Okay. So kappa nu d is max. You modify this part a little bit. Okay, actually, so we are using Q divisor. So it's K H0 MD plus A. So A is some sufficiently ample Cartier divisor. Okay. M to the K. And again, if this is all zero, you get you just put minus infinity. Okay. So A is some sufficiently ample Cartier. Okay. Okay, so what I'm going to do is I'm going to generalize this to the pseudo-effective case. Okay? So the volume also has some meaning, and the dimension has also meaning. The dimension actually catches this numerical Ithaka dimension, not this one. Okay, so some properties. So if D is big, then kappa D and they are both equal to the dimension of the variety. Okay, so here N is actually the dimension. So you can put kappa here. Okay, because N is this. Okay, so in the big case, it actually catches the dimension. The numerical Ithaka dimension or Ithaka dimension. So this is first property, and kappa nu is the numerical property. This means that if you have two numerically equivalent divisors, then you get the same numerical dimension. But actually, this is not numerical. Okay? This is not. Okay? And of course, which is bigger? Because we added ample divisor here. So actually, this is larger in general. Okay? And in the original construction of the Okounkov body, this satisfies the numerical property. So what we are trying to do is to extract this numerical dimension, not the original Ithaka dimension. Okay. Extract rather than, because this is not numerical. This is a numerical invariant. Okay, and the original construction was so the original Okounkov body was a numerical object. So we want to extend this result by extracting this dimension from the Okounkov body. How we define this? So this is the integer k. I'm sorry. sorry. The m lim sup is, sorry, I forgot to put the limit. So it's important. Okay. So to extend the Lazarus-Perret-Mustafa's result to pseudo-effective divisor case, we had to modify the definition a little bit. So we call this the limit. So it's basically this. So D is a pseudo-effective divisor. Okay, and we know that if you add some ample divisor to pseudo-effective divisor, this becomes a big divisor. Okay, the sum of pseudo-effective divisor and ample divisor is always big. So we can construct this Okounkov body using the original construction. Okay? So A is ample and epsilon is positive. So this is a big divisor. And we construct it using the original construction. And we take the limit. Okay? And this is called the limiting Okounkov. So this is the definition. And this actually catches the dimension of this is actually equal to the dimension of the numerical dimension of the divisor D. And we can also give some meaning to the volume of this lower dimensional Okounkov body. So here is the theorem by me and 3 other collaborators. This is the generalization of Lazarus-Perret-Mustafa's result I just erased. So this is pseudo-effective. Okay. Then for some flag, not all flags, so for some flag y with yn minus kappa nu d. So I will fix this notation. This is a sequence of irreducible subvarieties. But at some point, yi is equal to the dimension of yi is equal to the numerical Itaka dimension. And okay, so this means the dimension of V is the numerical Itaka dimension. For some and the volume of xv, and I will define what this restricted volume is. So you may have seen volume x restricted on V, but we have plus sign here, extra plus sign. So D is positive. So for some flag which satisfies this, then we have the dimension of the emitting body. D is precisely this dimension. You can compute the dimension of this. Okay, so the dimension of this limiting Okounkov body is actually equal to the numerical Itaka dimension. And as you said, you can still compute the volume with respect to the the space. So the volume of this now. So now we know that the dimension of this Okounkov body is this one. So you compute this in this space. Okay. Then this is equal to, so the statement is similar. So volume of xv plus d divided by kappa nu factorial. Let's say kappa nu d factorial. Okay.
Now, I have a question. So, is this subspace where the Okounkov body lies is a rational slope?
Rational.
Rational slope? I mean, otherwise I don't understand how you compute. What's the volume in subspace?
Here. So if this is R2, then the limiting Okounkov body may look like this.
If it's a rational slope, then I understand that. If it's not a rational, what's the measure?
Even if this is non-rational, you can still compute the length. Length has some meaning. Right? Yeah. So the rationality doesn't matter. Even if the slope is irrational, you can measure the length. Right? Okay. So of course, I said this is a generalization of their result. So if D is big, then we can recover the full statement of the original statement. Okay. So now what I have to do is I have to define what this is. Okay. So as a remark, so if D is big, then recover. So then the numerical dimension just becomes n, and this recovers the whole statement. So I need to explain what this is. Yeah. So I already defined what volume is. Okay. So first we need to define this restricted volume. So for simplicity, let's assume that this is Cartier. Okay. So in this case, And let's say the dimension of V is D prime, let's say, N prime. Okay. And this is subvariety of X, and this is lim sup the dimension of H0 and D. Let's put X and D. The restriction map. And N prime and prime. This is the restricted volume. Okay. So you restrict the sections on V, and you compute the dimension, and you do it similarly with the usual volume. Okay. And what is plus? So we called it the augmented restricted volume, but you can call it whatever you want. But so this is the volume, the limit of epsilon 0 into volume xv d plus epsilon a is some amplitude device. Okay. Okay. And this is independent of the choice of amplitude device. You add a little bit of amplitude divisor and you take to the limit. Okay. This is the augmented restricted. Okay. So actually we didn't invent this in our paper. This already appeared previously. So main result we use in the proof of our theorem is the following lemma. Brian Lehman's. He studies the Itaka dimensions and studies many other equivalent characterizations. Okay? But I heard some of them had some errors, but this statement should be okay. So mu d is the maximum of B, dimension of B, and volume. Is volume. So the key result we use is this one. So this is the key result. Okay. So basically, so in this flag, so this B has dimension which is equal to the numerical Itaka dimension. So basically, the basic idea is if you restrict D onto the subvariety which computes this dimension, behaves like B. Big device. Okay. So idea is to restrict everything to the big case, and we use the original Lazarus-Feldman-Statats result. Okay. And apply big case. Okay, so actually I wanted to say something more about the proof, but I think this is, I don't have time. So and last thing, so So we had two dimensions. One is the numerical Ithaka dimension. The other one was the usual Ithaka dimension. Actually, we can also recover the Ithaka dimension too. If you take the sufficiently general the admissible flag, you just remove this limit, and this becomes the usual Ithaka dimension. And here you just erase the positive sign. Okay? And if you take the sufficiently general admissible flag, then you get the similar statements. Okay? But I want to have some numerical property, so that's why I stated this first. Okay, so today, I talked about the volume of the Okounkov body and the dimensions of the Okounkov body. So tomorrow we will extract some local information. So if you have a flag, then the last one was a point. And we focus on this point. Okay? So if you vary this point, then you get some local information, local positivity, like Seshadri constant and the base locus. You can even extract the base locus, which is called augmented base locus and the diminished base locus. Okay. So tomorrow we will focus on some local properties. So this is some global properties. Okay, so I stop here today.